Yeah, so we are going to look at this problem of counting inversions, and before we give the formal definition, let's look at this like problem that we might face in some real world situation. That so these are suppose movies, and two people are ranking these movies. Okay, so P1 ranks these movies that okay, A is his or her favorite movie, then it is C, then it is B, then it is E, and then it is D. And for P2, the order is B. The B is the favorite, and this is the second, this is the third, this is the fourth, and this is the fifth. Okay. So now we want to find out how to compare these rankings. How similar they are. So how can we do that? Any suggestion that how we can compare these two rankings? So there are these two rankings. Two people have. So we might right. Okay, we have some website like IMDb or any such thing where people give ratings, and then we want to compare people's ratings for some reason. So how do we do that? Any like suggestion for how we can go about comparing two rankings?
So for every pair of movies, we can check whether the first person has put the first movie as his priority, or like the similarities between every two movies.
Yeah, the similarities between every two movies. So let's make what Manish said slightly more formal. That what we are going to do. So what we'll do, we'll arrange the movies. Let's say in the first person's priority order. So let's put so first person. So let's call it 1, 2, 3, 4, 5 because we are going to put the movies in that order. What is the first movie for first person? It's A. Second movie is C. Third movie is B. Fourth movie is E, and fifth movie is D, right? And now write down what is the ordering of these movies for the second person. So for the second person, A is second, C is fourth, B is first, E is third, and D is fifth. Okay. So now this is like okay. So this is the order of the first ordering of the first person, and this is if we look at we just put that okay what is the second person how did they look at it how did this so this is the ordering of the second person of these movies which are ordered by the first person's list. So now what we can do as Manu was suggesting that for every pair that is that okay so now this movie was ordered number one here by the first person. So we can look at every pair and see how many times it gets flipped. So this, so let's draw a graph or just match these numbers. So 5 and 5 are fine. That is not a problem. Okay. If you look at 5 and 1, 5 and 3, 5 and 4 will also be fine because there is no flipping there. But now if you look at 4 and 2, again they are fine because relative ordering of 4 and 2 in both the things remains the same. The relative ordering of whatever movie is there, basically. So here now the conflict is between, and conflict can be found exactly by looking at the number of crossings here. So what are the conflicting points? Let's say we want to find these pairs. So here there was some movie. Okay, let me write movies also. Why did I remove the movies? So suppose whatever. So first is A. We use a different color. A was here. Second was C. C. Third was B. Fourth was E. And fifth was D. Right. So there is a conflict between A and B. Let's say. right? Because the first one ranks A as 1 and the second one ranks A as 2 and B as 3 and B as 2. So here itself we see the conflict that it gets reversed. Some relative ordering gets reversed of these two elements, right? Similarly, there is a problem between A and whatever is here. Uh, so this 4 is, so what is 1 here? Okay, so we are actually looking at the E. So A and E. But then, yeah, so again, A and E are ranked 1 and 4 here, but they are ranked 2 and 3 here, which is fine, I guess. So that is not the problem. What is the problem? We'll find the problem looking at these guys. Is 4. Yeah, so there are movies. Okay, so instead of looking at the movies, actually we are looking at the number of inversions in the sense that how many movies or how many rankings get flipped, not how many movies get flipped. So that is why maybe I should not have written it, and that's why I was doing the right thing. That how many pairs of rankings which are there, which get flipped. So here, what is one pair that gets flipped? That is 1 and 2. So 1 and 2 gets flipped. Then the other pair which gets flipped is 1 and 4. Then 1 and 3. No,
3 and
sorry.
4.
3 and 4. Okay. So now, since we are comparing these, there is one way of writing this thing. So since this is in order anyway, we can forget about this one and we can abstract out problem even more. And what we can say is we are just given n numbers, a1 to an. Okay. So we are just given a list a1 to an. And what do we want? So this now we will take to be implicit. The first ranking will take to be implicit. And what we are going to say that what is going to be the like definition of inversion now? So now we are given suppose the second list and we want to find out such conflicting pairs. So there are three pairs. What happened? So there are three pairs, for example, in this case. So now we want a more mathematical abstract definition of this. So how do we write it?
AI is greater than AJ, while I is less than J.
Yeah. So an inversion happens when, or inversion happens for AI for ij if I is less than j, but AI is greater than aj. So I and j are the indices that maybe correspond to the first list, first ranking, and then this AI aj is actually the second list. And if you have a number like 4 and 1, then this will be problematic because they are ranked somewhere else. Okay, good. So yeah, B and C were actually the problematic parts. From the second one, I should have chosen the things because B and C are ranked 3 and 2 for the first and 4 and 1 for the second. Anyway, so you can figure this out. Good. So, all right. So we have this quantity now, and we want to find out that how many such inversions are there in a given list. So let's just get something that what is the minimum number of inversions that can be there? 0. When the list is sorted in ascending order, right? And max is What is the value of max?
NC2.
NC2 when sorted in descending order. Why? Because now if the list is sorted in descending order, then you look at any pair ij, then of course AI is going to be any pair ij says that I is less than j, then AI is going to be greater than aj because the list is sorted in decreasing order, descending order. Right? Okay, good. So this is the maximum number, and how many pairs are there? So what can be a naive brute force algorithm?
Check for every.
Check for every. So just have two loops, which just like from one to n, and for all of them, just find out whether it is an inversion or not, and then just increase the counter, right? Okay, so this is order n square time because n choose two pairs, and for each of them, we can do in constant time. We can just go at that list and look at what is there at ith position, look at what is there at jth position, and that's it. Okay. Good. But now we want faster. Suppose we want order n log n. And we saw that for order n log n, we had this strategy in the last lecture. We saw that how we could achieve order n log n. We could achieve yeah. So we could achieve order n log n by dividing the input in two equal parts, solving them recursively, and then combining them in order and time. Right? This is what we know, that if we can do that, then we can achieve order n log n time. So we want to make this order n square brute force algorithm faster, and we want to do this by going through this paradigm. Okay, so let's see. So what do we mean, or what do we want to do? So basically, we look at the list. So let the list be A1 to AM, and let AN, and let M is equal to whatever n over 2. Let's take the ceiling. So let's divide it into two parts. Here it's AM, here it's AM plus 1, and now what we want to do, let's call it A, let's call it B, and so call the procedure recursively on A and B. Okay, and basically to find the number of inversions. In A and B, and then somehow combine them to find the inversions across. Okay, so there are some inversions inside this, the first part. There are some inversions which are inside the second part that we find recursively, and now we have to combine them. Like recall merge sort. That okay, we have recursively done the sorted the list, and now we want to combine the list, right? So we want to do something similar here. So yeah, and we want to combine them in order and time. Right, and this does not seem to be a very easy job. That okay, how do we go about it? if we have just solved it recursively, we just have this number that okay, whatever some small a is the number of inversions here, small b is the number of inversions here. But how do we use that, or how do we use that to find the number of inversions in uh, which are going across in linear time? So because okay, so what are the inversions which are going across? How do they look like?
The left part of the array has a smaller element than the right part.
Left part of the array has a bigger element than the right part, right?
Yeah.
Yeah. So exactly. So across inversions, how do they look like? Left part or A, let's call it A. A has an element that is bigger than, or let's say even more formally. So what are these across inversions of the form? They are of the form, let's say, AI, AJ, such that AI is in A, AJ is in B, and AI is greater than AJ. Okay? And why will this be an inversion? Why is this an inversion? Like, I mean, the answer is trivial, but still, just to confirm that this will surely be an inversion whenever this happens.
Because A has all of elements of A have lower indices than all elements of B.
Exactly. Because all the elements of A have lower indexes. Then, so if AI is in A, then and AJ is in B, this implies together that I is less than J. And then we have that AI is greater than AJ, so this is going to be an inversion. Okay, so these are the across inversions, and these are the only across inversions that we need to find out. But then again, both of them have size n over 2, and then how do we do this in linear time? Okay, because we don't know. We just know how many inversions are there inside A and B. We don't know anything else recursively. So, what can we do? Any any suggestions or any ideas? If we can do something to figure this out, that okay, how many are these across inversions?
If they are already sorted, we can count inversions.
Good. So if they are already sorted, then we can count the inversions. So we'll see. So the idea is that if A and B are sorted, then it is easier somewhat to count the inversions. Okay. So recursively, also sort. Don't just count. And then, so suppose now that recursively we have counted and sorted. So let's say then how how do we do this? The merging part. Okay. So now we have the list A, we have the list B, and then we want to make a new list C, which is the sorted and merged version of A and B. Okay, fine. So you have the number of inversions inside A, and also you have sorted it. After sorting, of course, there is no inversion in this new list, but you have just sorted, and you already know you have stored in a variable how many inversions are there inside. Okay, so now the question is, how do you get this C? How do you count the inversions? by in order and time. That is the important part. Otherwise, you can just go through every pair of indices and see whether they count an inversion. So you get whatever n over 2 whole square, something like that. But we don't want that. We want order and time. So how do we do this? Again, let's go towards the idea which is similar to the merge sort idea, that we have this current pointer in both the lists. So suppose this first element is A1. This first element is B1. Okay. And again, we'll do, since we have to sort, we'll do similar to what we did in merge sort. So whatever is smaller, we'll put here. So suppose if A1 is less than B1, then we will put it here. A1. And we'll see, whenever we put something in C, we'll see that, okay, how many inversions are involving that element. So if we put A1 here, are there any inversions involving A1?
No.
No. Why? Because how did the list look like? B was here. In the original thing, B was here after A. So whatever the smallest element of B is, whatever the smallest element of B is, suppose it was here, whatever, that is still bigger than A1. Right? So that means A1 might be occurring somewhere here, wherever, but whatever the smallest element of B is, that is still bigger than A1. I mean, I'm saying it might be occurring here as in position wise in the original list, it might be occurring here. So the smallest element of B is still bigger than the, A1, which is the smallest element of A right now. But that means that no other element can also be smaller. So that means these elements will always be in the correct order with A1, all the elements of B. So that's why A1 cannot give rise to any inversions. So we will put A1 and we will not, increase anything. Similarly, so whenever we will be putting anything from A from the current pointer, that will be fine. That will not be causing any inversions. But now look at B. If you put B1, then how many inversions will it cause? So suppose it was initially just till A1 only, and it was not that A1 is less than B1, but we have that B1 is less than A1. Then how many inversions get caused by B1? So we'll be putting B1 here, right? So,
Size
but
of it.
One.
the size, right? So whatever M, because A has M elements. So whatever size of it, right? Good. And what if the current pointer was somewhere else? Suppose we have added. Okay, so let's just we can go slightly slow because I don't want to start something new later. So suppose we had added first A1 and now A2 turns out to be smaller, then bigger. So first we have added A1, and then now we are adding B1. Then
M minus 1.
n minus 1, whatever, size of A minus 1, right? Yeah, good. So, so what does that mean? That okay, now suppose some element there is, here at some ith position in B, and then so the current pointer is here, and here the current pointer is here. So suppose it is at AI and BJ, right? And the comparison is happening. And if AI gets added, no new inversions. And if BJ gets added, how many inversions? M minus I, right? Or size of A minus I. Suppose the indices are A1 to size of A subscript size of A and B1 to B subscript size of B. So I mean M is the first in
Sir,
the first
why
equation.
no new? Why are there no new inversions when AI is added?
So let's go through that again. Good. So when AI is being added here, so what did we want to calculate? We wanted to calculate. So initially the list looked like something, so this is the sorted order, but we want to find in the initial list how many inversions which are there which go across, right? So now for the ones going across, what do we want? That this value is bigger than this value. The value of something in A1 is bigger than the something in B, right? In A is bigger than something in B. That is what we saw. That across inversions, how do they look like? There is some AI belonging to A, and there is some AJ belonging to B, such that AI is greater than AJ. That is how the across inversions look like. So now, when A1 is being added, okay. Oh, is your question about A1 in general or AI? You're not able to understand the middle in the middle what is happening.
I can understand A1 because A1 will be the smallest, but not AI.
Good. Okay. So suppose A1 is the smallest, right? Now, but we have this C list always sorted, right? So whenever I'm adding some element of B, let's say when, for example, let's say that. Okay, so let's take A1 and A2, and that might give you an idea. So A2 might be part of some inversions, right? How? Because now, like B2, B1, A2 might itself be an inversion. So A2 might be bigger than A2 might be bigger than B1, let's say, and this is an inversion, right? But suppose after this A2 gets added. Okay, good. So A2 is part of the inversions. What inversions A2 can be part of? Or whatever, some AI, if you want AI, what inversions AI can be? Where do those BIs lie? Or what is the relation of AI with those BIs? AI has
They
to
have
be greater than
already been
BI.
added.
They are already added here, right?
Yes.
So whenever AI is considered, all the inversions that AI is part of are already added and counted for that BI.
Achha, okay, I got it.
So, so these BIs, so that's what. Whenever AI gets added, so there are no new inversions or there are no remaining inversions that involve them. Whatever inversions they were part of have already been counted for the BIs that you have added to them. Okay.
Yes, sir.
So yeah. So now you. So whenever you add the BJ, then you have that the number of inversions in AI which are left are or which get in which BJ is involved is the number of elements which are left in A. Okay, so, which is A minus I. Good. So this is the thing now we want to do, and
So
that
it would be a minus I plus 1, right?
Yes, sir.
yeah, okay,
Doesn't make
fine.
it.
I mean whatever number of elements
Yeah.
are left. Okay. Okay, so that is it then. That is for the that is for the merge. So let's call this procedure merge and count. Okay, and what is going to be let's say the original thing that is going to be sort and count. Sort and count. What will sort and count do? Sort and count will take the original array, divide it into two parts, and then call sort and count on the individual parts. And what and then whatever they return, sorry, yeah, and whatever they return, then it will perform merge and count on that. So let's look at the first, like the sort and count procedure. What does it do? If the list has, yeah, if the list has one element, then there are no inversions. So this is just the base case, right? And then it says that divide the list into two halves. So the first half has n over two elements, the other half also has n over two elements, floor and ceiling to adjust, like so that every element goes into one list only. And now, what is RA comma A? RA is the number of inversions in list A. So that recursively this sort and count algorithm returns. Similarly, this is RB is the number of inversions in B, right? And now what happens after we get this sorted list? So this A is actually, so this A that gets returned is actually sorted. This B that is getting returned is sorted recursively, okay? And then what do? We do merge and count A and B. So merge and count is what we saw earlier. I'll come to that. So merge the lists A and B to get sorted list L, and this R is the number of across inversions. Yeah, Mr. J, is there a question? No? Okay. Good. So this is what we do, and then we do this. We add the numbers that this is the number of inversions in A, this is the number of inversions in B, and these are the cross inversions. So return all the sum of all the three. Okay. So this is the sort and count procedure. Now let's look at the merge and count. Again, it's exactly the same. So maintain a current pointer into each list. So as we said, we have two lists. Maintain a current pointer, right? Initialize to the pointing to the front elements. Maintain a variable count, like where you will have the so count is what you will return as the number of inversions which are across. For the number of inversions, initialize to 0. Now, while both lists are non-empty, let AI and BJ be the elements pointed to by the current pointer. So instead of this, let's say the current pointer is here, current pointer is here. So this is AI, this is BJ. Good. And if now, if BJ is the smaller element, then increment count by the number of elements remaining in A, which is these many, whatever the size of A minus AI plus 1. Okay, and then we end that if. So yeah, it does not. Yeah, append the smaller of these two to the output list. So it says that append the smaller of AI and BJ to the output list. So you have this output list, which is the list C. Append the smaller AI or BJ, whatever you have. And if AI is the smaller one, then you don't have to do anything. If BJ is the smaller one, then you need to do something. So if BJ is the smaller one, then you increase the count as we saw, and then advance the current pointer by 1 in both the lists. No, sorry, in the list where the smaller element was selected, because the other list remains the same. So the current pointer gets advanced from wherever it gets selected. So AI gets selected, then it goes here. BI gets selected, then it goes here, the current pointer. And that's it. You go through till one of the lists are empty. If one list gets empty, then append the remainder of the other list to the output. So after, suppose A gets empty, then fine. Then only thing left is B, and they are not going to cause any inversions because there is nothing left in A. And if B gets empty, A is left, then again those elements are if B gets empty and A is left, then those inversions are also counted for these elements of B, and that is why you can just append the end of A to this list. Okay. So if any of them gets finished, you can just safely append, and the count will be fine. Now you return the count and the merged list. So return count. So that is what, like whatever this R and L that we had in this thing, that gets returned by this procedure, right? So let's look at the running time. Okay. So what is the running time? So here, this is just whatever initialization. This is whatever. So this is, of course, order one time, because this is just one variable. This is also actually order one because you are just putting a pointer to the front of the list, not really anything. Now this is the while loop. This is the main thing, right? But all the operations, what are the while loop operations? While loop operations are that you compare the elements and which are pointed by the pointers anyway, so you can access them in order one time. You just like find the smaller one that can be done in order one time. Then you just add that to the list C, which also has a current pointer, of course, because you are appending it. So that also is order one time. And increment the counter by one, order one time, advance the current pointer. Sorry, increment the count by not one, by the number of elements. But this number of elements also you can find in order one time by just decreasing from A, size of A, the number I or plus one, whatever. This number you can find in order one time. So every step of the while loop takes order one time, right? And how many times the while loop runs? While both the lists are non-empty, and every single time what is happening in the while loop, one pointer gets advanced by one. Either the A pointer gets advanced or B pointer gets advanced, right? So the while loop runs at most order n times, or where n is the sum of the number of elements in A and B, right? Good. And once the list is empty, append the remainder of the other list to the output. Again, so this was the max number of times it would have run the while loop, because while loop might finish. But even this is order n time, because remaining you just, even together they will be order n times, because for each element you will be spending constant number of time. But anyway, you can say this order n and this order n, that is also again fine, and then you return. So this procedure takes order n time. This merge and count procedure takes order n time, as we had already seen before. But still, like, just to go through the algorithm more carefully and see that, okay, it actually takes order n time. Okay, what about sort and count? Sort and count now takes a list of size L, I mean a list L. Suppose L has size n. Okay, so now we write the recursion for sort and counts running time. So what is Tn? Tn is equal to 2Tn over 2 plus order of n. Why 2Tn over 2? This is, we are applying recursively the same algorithm. This is applying recursively the same algorithm on half the size. So that is why we get 2Tn over 2 plus order n for this. That we just showed. That merge and count takes order n. So this is the recursion that we get for this part. And we know that this will, and then we just sum. So yeah, that can come in order n. And then we just sum these numbers. So total, we know how this recursion gets solved. That we know that Tn is equal to order and log n. Right? So we get the theorem that whatever. The algorithm sort and counts the number of inversions correctly and runs in order and log n time. Okay. So this is the problem that, like, yeah, I wanted to do today. We went slow through it because again, like, starting something at the end might not be very. I mean, I might give just the problem definition. Is there any question about this particular algorithm? I mean, any part, the merge and count part or the sort and count part. Okay, if not, then there are like 5 minutes left. I'll just go through the problem definition of what we'll be doing in the next lecture, okay? Because that might take more time, so we can save a little bit of time by just going through the problem definition. In the meanwhile, if there is any questions about this, then please ask. Okay, maybe not. Okay. So the problem that we'll be looking at in tomorrow will be closest pair of points. So given n points in a plane, find the pair that's closest. Okay, so again, what is going to be brute force? And choose two pairs are there. Find distance between all of them. Find minimum. Put them in a list if you want, or just keep doing it and keep the minimum. And okay. So that takes order n square time. But like the previous thing, again, we want to do it in order n log n time. Okay. So let's just make it slightly formal. What is the input? Just the input instance. That P is equal to, let's say, P1 to Pn are the given set of points. And Pi is Xi, Yi, let's say. And now for Pi, Pj, d of Pi, Pj is Euclidean distance. Euclidean distance between Pi and Pj. Okay. And the goal is to find Pi, Pj, I not equal to j, such that d of Pi, Pj is minimum. Okay. So tomorrow we'll look at this particular problem, and there is one assumption that we'll make. That all the x and y coordinates are different. We'll see how to get rid of this assumption also, but like you can just rotate the given set of points very slightly, and then that will make all the coordinates different, while the relative distance of those points will not change. Okay, good. So that's it. I just wanted to give the problem definition today. If you want to think about it, you can think about it. So the brute force takes this much time, n square time. We want to do that in order n log n time. And again, we'll be using divide and conquer to get to a better running time. Okay. So any questions about this? I don't think so, but still in the problem statement or anything, if there is any question, then you can ask or about the previous thing or in general. Okay, cool. So if not, we can finish today, and yeah, I can finish on time for once. So thank you all for coming, and see you tomorrow.